Hi, grade 9s. Welcome to the first lesson in the Unit 2 work for your grade 9 academic math course. This unit is called Powers and Polynomials. So we're going to be reviewing some of the algebra that you would have learned in grade 7 and 8 and extending that to be able to work with more complex algebraic expressions. The first day, we're going to be talking about powers, which is expressions containing an exponent, and we're going to be looking at those up to a degree 3. And we're going to talk about what that terminology of the word degree in terms of math language, what that means. So there is a fair bit of terminology in this lesson. The first example here that I want to look at with you is to define or give an example of 6 common words down here. Now, some of these words are sometimes misused or used interchangeably when really they have pretty distinct meanings. So above, you see that there's 6 different expressions, and a certain part of that expression has been highlighted in each one. So the first one we're going to look at is A, which is a variable. So if you guys can look up here at those 6 things, which one looks like it has a variable highlighted? Probably most of you guys are pointing to or thinking about that first one. We've got the X highlighted in each spot in the first expression. And remember that a variable is a letter that's used to represent a numeric quantity. And that variable can change and take on different numeric values. So this one is A. That's a variable. The next term we're going to look at is called constant. So a constant is really the opposite of a variable. A variable can change and take on different values, but a constant is a number that just stays the same. It has the same value no matter what. And if we look at kind of the different expressions here, I see number 5, or this V, that 2 is highlighted. A 2 is a constant value. 2 always means the same thing. X could mean different things depending on the situation, but 2 has a constant meaning. The third one is power. So I'll kind of check these off as I go. Some people mix up power and exponent. So a power refers to the whole expression with a base and an exponent. So a power is going to be this one, 2 to the exponent 3. The whole thing together is a power. The next one, base. In a power expression, so in a power, the base is the big number that the exponent is raised to that given exponent. So the base, we see here, just the 3 is highlighted. That 3 is going to be my base. The opposite being the exponent, so that's a small number that indicates repeated multiplication. And I know that you guys have seen those exponents in grade 7 and 8 as well. So here I have an exponent of 2 that's highlighted. So this one here is exponent. And the last one, I only have one left, and this says algebraic expression, and here the whole thing is highlighted. So this combined, we've got a number, a constant value 5, multiplied by a base of x to an exponent 2. Lots of different stuff going on here, but all of this together can be called an algebraic expression. So I hope you understand those. Make sure that you kind of take a look and review those different terms, because you will need to know them to be able to complete your work throughout this unit in the course. A few more definitions here. The first one, a coefficient. The definition of that is the factor by which a variable is multiplied. Now we're going to look at some examples of this, but the terminology there, that's the mathematical definition. But really, what this means is it's whatever number is multiplying a variable in an expression. So say, for example, you had the algebraic expression 3x squared. The coefficient is the number that you're multiplying that variable part by. So the coefficient is the 3. If you had the expression 5a, the coefficient is the 5. So it's the number out front of your variable part of your expression. And you can have in an algebraic expression, you can have multiple coefficients. I'll do an example with multiple terms here. We might have an expression that was 10x squared minus 4x. Here we have two coefficients. We've got a coefficient of 10 on our first piece and a coefficient of 4 on the next. Those would both be considered coefficients. Okay? And I kind of touched on this in the last one, but the next definition is term. So a term is part of an algebraic expression, often separated by addition or subtraction signs. So if we had a bigger algebraic expression, sometimes algebraic expressions like 3x squared or 5a, they have just one term. Lots of the expressions that we're going to be looking at in this unit, though, have multiple terms. So this has 10x squared, that's one term, minus 4x, that's another term. Their terms are separated by a plus or minus sign. So I'm going to do an example here. We might have an algebraic expression that was 6x cubed minus 4x squared plus 7. This algebraic expression has three terms. So we've got a term that is the 6x cubed, and then a term that is the 4x squared, and then a term that is the 7. This algebraic expression has 1, 2, 3 terms. So an individual term is the piece of the expression that's separated from the rest of it by a plus or a minus. Okay. A polynomial is an algebraic expression that contains monomials. So to explain what this is, we need to know what a monomial is. A monomial is an expression with just one term. So looking back to the first one, 3x squared, that's a monomial. 5a, monomial. It has just one term. So if it has just one term, it's a monomial. If it has a polynomial, it has multiple terms. There's a couple more specific words that we're going to get to in the next slide. So a monomial is a single term, and a polynomial means more than one term. So here, monomial, again, is an expression with just one term. So examples of that might be 3x squared, 5a, negative 7y to the exponent 5. Each of those are one term. And this is not one example, it's 3 different examples. A binomial is a specific kind of polynomial where there are 2 terms. So an example of a binomial might be 4a plus 7b. That's a binomial because it has one term, 2 terms, separated by plus or minus. Another binomial might be negative 2x cubed plus 5x. So that's a term there, the negative 2x cubed, and then the 5x is another term, 2 terms. A trinomial, kind of following again the same pattern, that's an expression with 3 terms. So here you might have 4a minus 3b plus 2c. There you have 1, 2, 3 terms. Another trinomial might be x squared minus 5x plus 7. X squared is a term, 5x is a term, and 7 is a term. They're separated by the plus or minus. So that's a trinomial. If we get to more than 3 terms, often I'll get the question of what happens if you have 4 terms. We don't give it a special name. Past 3 terms, we just say polynomial. The last definition here is of degree. So the degree is the highest exponent of any term. So I'm going to look at a couple different examples of polynomials. So if I have negative 3x plus 4x cubed plus 5x squared. If I wanted to look at the degree, I need to find the biggest exponent on my variable. So here, this doesn't have an exponent, so that's a default kind of 1, and we'll talk more about that later. So this is the biggest exponent, is 3, so that means that the degree of this is 3. You can have really big degree expressions. We might have 10a to the 7 minus 4a to the exponent 12 plus 3a to the exponent 20. You just look at the exponents on each variable and find the biggest one, and that's your degree. So there, the degree is 20. The one trick with this is if you happen to have multiple variables, so different letters, in an expression. So one example that I might do, what if I had 2x squared y cubed minus 4x5y squared plus 3x y squared. Now remember, if we don't have a variable or an exponent on our variable, it's just a 1. There's just one x there. So here I have to look at the sum of the exponents. So here I have an exponent 2 and an exponent 3. In this term, the sum is 5. Here I have an exponent 5 and an exponent 2. So the sum of both together, the x's and the y's together, is 7. And here the exponents add up to 3. So we are going to circle that one as our highest. And we'd say that the degree of this one is 7. So you're just looking for the biggest exponent, and that tells you the degree of your polynomial. So we're going to talk about how we can represent what these mean in a diagram. So if we wanted to represent the algebraic term for t, I'm going to assume that t is some kind of measurement. I don't know how big t is, but I'm going to use my ruler and actually go up here, and I'm going to make t about 1 centimeter. So I'm going to call that t. So that measurement is t. If I wanted to do a diagram representing 4t, that would mean I have 4 times t. So multiplying this measurement, that length, by 4, I would just draw a line that is 4 times as long. So this would be broken up into 4 equal parts, each which were the same size as t. The next expression, 4t squared, here I'm going to have to look at a measurement of 4t, but then multiplied by itself. And squaring something, that's actually going to change the number of dimensions in my drawing. So that's not just longer, it's actually multiplying the length 4t by itself. So we're going to get a two-dimensional picture here. So here we would have to draw a square that each side of the square had a measurement of 4t. So this is a square with sides of 4t. The last one is going to be even a little bit harder to draw because now we're doing 4t cubed. And I know that you guys have done measurement problems where you had something cubed, and that would be a volume question. So that's going to be a three-dimensional shape. And I'll see if I can draw this accurately enough. We are going to take our 4t squared and multiply that by a kind of thickness of t that's going to go into our third dimension. So we're going to try and draw a cube here with measurements of 4t. Whoops, I'm going a little bit over there. So here I've got here I come up with a cube that means 4t times 4t times 4t. So that would be the volume of this cube with 4t times 4t times 4t. And that's what cubed means. It means times itself. 3 times. So this length times this length times this length. Squared means times itself once. Okay. This is kind of working backwards. This says the area of a square tile is 116 centimeters squared. We want to determine the length of its side to 2 decimal places. So here I'm going to draw a diagram. And I know I have a square shape, and I know that you guys have done area of two-dimensional shapes a lot in your elementary schools. So for sure you guys have seen that the area would be length times width, or for a square in particular, it would just be the side length squared. So usually we would label the side with an S for a square. I'm also to note that this is a square. I'm just going to put a little tick mark on each side. I may not have drawn this perfectly square, but this shows that all 4 of these sides are equal. So we can see that it is in fact a square. So we know that area is the side length squared. Now, lots of times in elementary school, for sure, you would have been told, oh, here's a square and this side is 5 centimeters and this side is 5 centimeters and what's the area? And you would do 5 times 5 is 25 and make sure you put your units. But here, this is giving us the opposite thing. It's giving us the area and we have to figure out the side length. So we know that 116 centimeters squared is equal to the side length times itself. And we have to figure out what is the actual side length. So for this, I want you to make sure that you have your calculator. And I have 2 different calculators here, and I want you to pull your own calculator out and make sure that you can use it to do this kind of question. The first calculator I have here, I would have to put, we know that to undo that squared, the opposite is the square root. So I'm going to write this down first. The side length is going to be the square root of 116. If you maybe have a new calculator this year, or if you haven't done this yet, I want you to make sure that you can find the right button. So on this calculator, I have a square root sign button, and then I have to type in the 116 and push equals. So this comes out to 10.770. So it says determine to 2 decimal places. I'm going to put 10.77. The next number was a 0, so that won't round up. And I always want to put that dot above the equal sign to indicate if I rounded off. So that may be how your calculator works. If it's not, some people may have a different kind of calculator. And this one, for instance, if I push square root 116 equals, it just says 116. I don't know if that's clear on there. So this calculator goes in the opposite order, and it's just kind of trial and error which one yours is going to be. This calculator, you have to push 116 and then the square root, and it also comes out to 10.77. So it's just a bit of trial and error. Use your own calculator. Get used to the calculator that you're working with. I would discourage you from using your phone as a calculator, even though it's probably right in your pocket or in your lap more often than your actual calculator is, because we won't be able to use your phone on a test. So please get used to the calculator that you'll be working with, and you may have to type that in different ways than your friend or than another person in class, depending which kind of calculator you have. One last thing that I have to remember here is that I have to put units. This was centimeters squared, so my answer would be measured in centimeters because that's the side length. Last example for this lesson. This is giving different shapes, and it's asking us to find the area of each square. So this is kind of a thinking one. On this one, we'll do this one first. It says that the area of that little teeny tiny square is 1. And we want to figure out the area of all of the other squares in this picture. Now, first of all, there's another square right beside it. So I know that that area there will be 1 as well. So I'm going to put in, try and color code things a little bit. I'm going to put in a 1. Because that, of course, is the same size. Now, what is the length and width of a square with an area of 1? Hopefully it makes sense to you guys that you're going to have a length of 1 and a width of 1. That square has side lengths of 1. So this square here, how far across is that measurement? That measurement there will be 1 from this square and then 1 from the next square, so that measurement will be 2. And all of these are squares, no rectangles. So if this is 2 and 2, that would be 2 there. Then that means 2 times 2 gives an area of 4. And we're just going to kind of work our way outwards. This next biggest square, we've got a length of 2 there and a length of 1 up there. So this means that that side is 3, doesn't it? So if this is 3 by 3, 3 times 3 is 9. Next biggest square over here. Let's figure out how far across this is. I know that this one was 1, this one was 1, and this one was 3. So that's 1, 2, 5. So this distance across there is 5. So an area of 5 and 5, 5 times 5, would have an area of 25. And we're just going to keep on working out bigger and bigger. Looking at this one here, we've got, this is a length of 5. Then we have a length of 1, so that's 6. And then this one was 2 more, so now we have 7 and 8. So this length here, up and down, will be 8. So this area, 8 times 8, gives me 64. The last one, this really big one in the bottom, we see that this part's 5 and we know that part's 8. So I think we can see here that this would be 13, 8 and 5 all the way across there. So 13 across times 13 across, this area here would be 169. And we don't know whether this is centimeters or meters. We're not really given units, so I'm not putting them in. But that's the area in terms of these little squares that are 1. So if you took these little teeny tiny 1 squares, you could fit 64 of those little 1 squares in that square. You could fit 169 of them in this square. It would be 13 of them going across and 13 up and down. So we're going to look at the next one here, a little bit different because we don't start with the smallest. So one important thing here is that these are all integer side lengths. So an integer, remember, is like numbers 1, 2, 3. It means no decimals. So if we look at this one that has a side length of 9, looking at the adjacent little tiny squares, I think that if we have to say this side length here would be 3, right? That would be 3 and 3 to get to the 9. So if that's 3 and that's 3, this little one must be 1. It can't be 2 because it's smaller than half, and it can't be a decimal. So if this is 1 and 1, 1 times 1 is 1. And same reasoning with that one up there. The next biggest square going out would be this one. So we know that's 3 and that's 1. So this would have a length of 4. So we're going to get 4 times 4 for the area of that square, which is 16. And similar reasoning here. We've got 3 and 1 is 4. That's going to be 16 as well. The next biggest square in here, we will have 4 across here plus 1. I see a 5 there. So 5 times 5 gives me an area of 25. And then the same here. I've got 4 and 1 is 5. And that gives me an area of 25. Finally, looking at these two, because they are symmetric, we've got a 5 up and down here and a 1 in there. So we've got 6 up and down there. That would give us 6 times 6 for the area, which is 36. Same thing over here. That's a 1 plus 5. So that would be 6 up and down there and 36. So this is a bit of a puzzle, but it's also good practice to work with your areas and your exponents, thinking about the square roots that will give you the sides and the squared numbers that will give you the area. So that's it for the Unit 2 Day 1 lesson. You guys are able to get started on your homework for Day 1, and the next lesson will be coming up as well.